On May 18, 2026, an asteroid will skim past Earth at 56,700 miles. That's closer than much of the hardware we've put in orbit, and astronomers found it days before it arrives. That's the part worth sitting with, not the flyby. Flybys happen. What's unsettling is the gap between discovery and arrival, measured not in months or years, but in days. The telescope pointed at the right patch of sky, caught a faint smear of reflected light, and the math came back with a delivery date that was basically now. The object is called 2026 JH2. It's estimated somewhere between 50 and 100 feet across, roughly the length of a 10-story building laid on its side. At that size, it wouldn't end civilization, but it would end a city block, or a neighborhood, or a ship at sea. It's not the kind of thing you'd want to find at the last minute. And here's where it gets stranger. 2026 JH2 isn't making this trip alone. In a single week, around 8 separate objects will pass inside the Moon's orbit. The Moon, which most of us think of as our distant neighbor, is actually 250,000 miles out. These objects are threading closer than that, some considerably closer, 8 of them, 1 week. Whether that sounds like a crisis or a coincidence depends entirely on what you know about the sky, and what you know about the surveys that are supposed to be watching it. Because the question 2026 JH2 is really asking isn't whether it will hit us. It won't. The question is how many of its cousins we haven't found yet, and what the window between discovery and arrival actually buys you when it's measured in days. Let's start with the number itself, 56,700 miles. The problem is that number means nothing in isolation. The human brain hears it and files it somewhere between far and really far and moves on.
So here's the comparison that actually lands. The Moon is roughly 239,000 miles away. 2026 JH2 passes at about a quarter of that distance. If the Moon were at the end of a football field, this asteroid crosses at the 10-yard line. Now consider where your satellite hardware lives. The GPS constellation, the network your phone pings every time you navigate anywhere, orbits at roughly 12,500 miles. Weather satellites, communications infrastructure, the systems that move money and military signals around the planet, those run at geostationary orbit about 22,000 miles out. 2026 JH2 passes beyond all of that, but not by much. Not by the kind of margin you'd call comfortable. It threads through a band of space that sits maybe 2 to 3 times further out than the satellites we depend on daily. Now think about what the object is. 50 to 100 feet. Call it roughly the size of a 10-story building, traveling at tens of thousands of miles per hour. Objects in this size class don't threaten the planet. They threaten cities. The Chelyabinsk impactor in 2013 was in this same rough neighborhood of size, and it shattered windows across 600 miles of Russian countryside and injured 1,500 people, and it didn't even hit the ground intact. So 56,700 miles isn't a number to shrug at. It's a number to hold still and feel, because the distance is only half the story. The other half is when we found it. We found it days before it arrives. Not weeks, not months, days. That's the number that should stop you cold. Not 56,700 miles, not 8 flybys in a week. The discovery window, the gap between the moment this object first appeared in a survey image and the moment it threads past Earth, is measured in days. And that gap is the structural problem sitting underneath everything else about this story.
Here's why it happens. Sky surveys are genuinely impressive. Programs like NASA's funded Catalina Sky Survey and the Asteroid Terrestrial Impact Last Alert System, ATLAS, scan enormous swaths of sky every clear night, looking for objects that move against the star field. They've found hundreds of thousands of near-Earth objects. The catalogs are real, and the work is serious. But the surveys have hard limits baked into their physics. Telescopes can only see objects that are large enough, close enough, and bright enough to register on their detectors. A 50-foot rock reflects very little sunlight. At distance, it's essentially invisible. It only becomes detectable when it's already on a close approach, when it's already almost here. There's a second problem: geometry. Some objects approach from the direction of the sun, inside the angle where ground-based telescopes simply cannot look without burning out. An object coming from that quadrant of sky is blind to current surveys until it swings around into observable darkness, by which point it may be days away. 2026, JH2 is not an exception. It's a demonstration. It's what the system looks like working as designed, finding a city-sized object with just enough time to track its path, but nowhere near enough time to do anything about it. The discovery is real. The warning is real. The question is what a warning measured in days actually buys you. And that's where the math gets uncomfortable. Here is what a few days buys you. You can confirm the trajectory. You can tell the public something is coming. You can watch it pass. That is the complete list. What you cannot do in days, or weeks, or even months, is anything that changes what happens next. Planetary defense, the actual kind, runs on years, not as a preference, as a physical requirement.
The only strategy we have that works is kinetic deflection, flying a spacecraft into the object early enough that a tiny nudge, applied far enough out, bends the path enough to matter. NASA's DART mission proved the concept in 2022. It hit the asteroid Dimorphos and changed its orbital period by 32 minutes. That is genuinely remarkable. But DART launched 11 months before impact and hit a target already well mapped and closely tracked for years. The deflection only works because the geometry gives you room. A small push early becomes a wide miss by the time the object arrives. The closer it gets, the less room you have and the more force you'd need. Against a 50 to 100-foot object arriving in days, you have no launch window. You have no spacecraft ready. You have no mission profile, no trajectory solution. Nothing staged. Even if you could improvise a launch in hours, which you cannot, physics won't cooperate. There is not enough distance left for a nudge to matter. So, the honest answer to what a few days buys you is situational awareness and grief counseling after the fact if things go wrong. For an object this size, hitting a city, that is not nothing emotionally. It is nothing operationally. The planetary defense community is clear on this. The minimum useful warning time for a meaningful response starts at years, ideally a decade or more. Days is not an early warning. Days is a countdown. A countdown, not a warning. Hold that distinction, because it reframes everything about the week we're actually talking about. 8 objects passing inside the moon's orbit in roughly 7 days. The instinct is to treat that as strange. A cluster, a coincidence, some unusual density in the near-Earth environment. But here's what the people who track these things will tell you. It probably isn't unusual at all. What's unusual is that we saw them. The sky looks crowded when you're looking. Most weeks it looks empty because the surveys aren't catching everything that's moving through. When telescope time increases, when a new instrument comes online, when coverage improves even slightly, the count goes up. Not because more objects appeared, but because we finally had eyes on the right patch of sky at the right moment. That's the uncomfortable reframe. The 8 flyby week isn't an anomaly. It's a glimpse of the baseline. This is what the inner solar system looks like with moderately good coverage. Take the coverage away, and those 8 objects don't vanish. They just pass unannounced. 2026 JH2 made the news because someone caught it days out. The objects we should be thinking about are the ones with the same orbital path, the same size, the same proximity, and no detection at all. Not a short warning. Zero warning. They cross inside the moon's orbit, and we find out afterward if the geometry gives us a trail to reconstruct, or we don't find out at all because they passed in the daytime sky or came from the sun's direction where no survey points. So the crowded week is actually a data point about incompleteness. Every object we spot this close is a proxy for several we didn't. The question isn't how many passed this week, it's how many passed last year and the year before, while we were looking somewhere else. How many of those missed objects are out there? The honest answer is that nobody knows, and that's the problem stated plainly. For asteroids larger than a kilometer, the ones capable of ending civilizations, the catalogs are reasonably complete. Decades of focused survey work have tracked down something like 95% of them. That size class,
we have a handle on. But a kilometer is not the only threshold that matters.
Drop down to the sub-100-meter range, the size of 2026 JH2, the size of the object that flattened 800 square miles of Siberian forest when it detonated over Tunguska in 1908. And the picture changes completely. Estimates put catalog completeness for this size class somewhere below 1%, not 50%, not 10%. Less than 1 in 100 of these objects has been found and tracked. That number needs to sit for a moment. A 50 to 100-foot rock hits the atmosphere with the energy of a nuclear weapon. It doesn't need to reach the ground intact to cause catastrophic damage. The air burst alone can level a city. Chelyabinsk in 2013 was smaller than this class, around 60 feet, and it shattered windows across 6 cities and injured nearly 1,500 people without anyone seeing it coming at all. A direct hit over a dense urban area from an object in this range would be a mass casualty event measured in hundreds of thousands. And we have located, by best current estimates, fewer than 1% of them. The rest are moving through the inner solar system right now, untracked, unnamed, crossing paths with Earth on orbits we haven't computed because we haven't found them yet. Current ground-based surveys weren't designed to close this gap. They're optimized for larger objects, and the smaller ones are simply too faint, too fast, or approaching from directions the telescopes aren't pointed. So here is the actual story of 2026 JH2. Not the one about a rock that almost hit us, but the one about a system that found it 4 days before it arrived and called that a success. Because in a narrow sense, it was. The telescopes worked, the orbit was computed, the all-clear was issued. No one needs to evacuate, and that matters. The infrastructure that produced this detection is real, and it is better than nothing. But 4 days is not warning time in any meaningful sense of the phrase. Warning time is a resource. It is the raw material from which every option in planetary defense is made, the thing you convert into deflection missions, evacuation orders, or at absolute minimum, the decision of where to point the cameras when the rock hits. 4 days buys you none of that. It buys you the knowledge that something is coming, and the helplessness of being unable to act on it. The objects that threaten cities aren't the mountain-sized ones we've spent decades cataloging. Those we mostly know. The threat that 2026 JH2 represents, the sub-100-meter class, fast, faint, arriving from blind angles, is the category where our coverage is measured in fractions of a percent, and our warning windows are measured in days when we're lucky, and 0 when we're not. The next Chelyabinsk won't announce itself. Neither will something larger. The gap isn't in our understanding of the physics or our ability to deflect an object given enough runway. It's in the runway itself. Warning time has to be built, deliberately, years in advance, with telescopes designed for this specific problem. Vera Rubin Observatory, Neo-Surveyor. These are the investments that convert the next 2026 JH2 from a 4-day scramble into a years-long known quantity. What this week's crowded sky is actually telling us is straightforward. The objects are there. They have always been there. The question is never whether one is coming, it's whether we'll see it in time to matter. Right now, for most of the size class that can destroy a city, we won't. That's the story. The rest is engineering.